Welcome back to another episode of HaugoMATH video. In this episode, I'm going to introduce you to my pet Trig-a-Saurus Rex. Yeah, he loves treats and loves going for walks. You know what, maybe I'll teach you a little about trig ratios along the way as well. Oh man, you're going to love my Trig-a-Saurus. He is so nice. So trigonometry is really working with right triangle geometry, taking the Pythagorean theorem one step further. And it's very similar to working with similar shapes. Like for example, here we have a rectangle that is 1 by 2. If this rectangle here is similar, being 4 by something, we can use the length-width ratio to help us figure out what the missing width is here. The length-width ratio is 1 to 2, or the decimal is 0.5. So, 4 over something needs to equal 0.5 as a decimal ratio. Well, that's got to be 8. So trigonometry is all about right triangles and the ratios of the side lengths. So before we discuss that, it's important to note that angle measurements determine how wide the opposite side is in a right triangle. Small angles make small sides. Bigger angles make bigger sides. And the 90-degree angle will make the hypotenuse, which is always the longest side. So with this 30, 60, 90 right triangle, this is a special triangle because it's exactly half of an equilateral triangle. And there's a special ratio of the sides opposite the 30-degree angle, the 5 and the 10. This side is exactly half of this side. So opposite over the hypotenuse is exactly 1/2 or 0.5. So once a reference angle is determined, then we can decide which is the opposite, the adjacent, and the hypotenuse sides. The sine function is a ratio of the opposite side over the hypotenuse side. Cosine is adjacent over hypotenuse, and the tangent function is opposite over adjacent. Saying SOH-CAH-TOA can help you remember this. These ratios are already predetermined based on the angle sizes, and are not going to be neat, clean fractions. They're mostly going to be decimals, and you can see all of them illustrated here in this table. Here we're going to see the cosine function in action, which is the adjacent side over the hypotenuse. You can see that ratio changing here. When we drag the point to an angle of 0, that means our adjacent side and hypotenuse side are exactly the same, or 1 over 1, a ratio of 1. And here we can see the point being dragged around the unit circle. Now we're up to our 30, 60, 90 right triangle where the adjacent side is exactly half of the hypotenuse, or 0.5 for the decimal ratio. And if we drag our angle all the way up to 90 degrees, that means our adjacent side would be non-existent or 0, and 0 over 1 for the hypotenuse would divide out to be 0. I almost got it to be 90 here, so we're pretty close to 0. And here we see the cosine function in action as it goes around the unit circle in the positive or negative coordinates. When we go in the counterclockwise direction, that's the positive direction. And if we flip that around to the clockwise direction, we are going in the negative direction. So we're always going to have our ratio fluctuate somewhere between -1 and +1. So that's why we get this curve-shaped graph for the cosine function. Here is the sine function in action, which is the opposite side over the hypotenuse. So here we can see the opposite and hypotenuse to be exactly the same, or 1 over 1, which makes 1. Here's our 30, 60, 90 right triangle where the opposite over the hypotenuse would be exactly half, or 0.5. And if we were able to drag that down to an angle of 0, which we're very close to, but half of a degree away, we would be at 0 over 1. The opposite side would be non-existent or gone, and 0 over 1 would make 0. So here we see the sine function in action and what that graph looks like down below. Same thing as we go in the counterclockwise direction, that's the positive direction. And if we flip that back around the other way, in the clockwise direction, that's going in the negative direction. Again, always fluctuating between the negative 1 and positive 1, and we get the curved graph again. And here we have the tangent function in action, which is the opposite side over the adjacent side. So, if we were to drag this down to an angle of 0, that means our opposite side would be 0 or gone, and the adjacent side is 1. So 0 over 1, 0 divided by 1 would be 0. And if we drag this point to a 45, 45, 90 degree triangle, this is half of a square, which means the opposite and the adjacent are exactly the same. The 0.707 divided by 0.707 is going to divide out to be exactly 1. And if we drag our point all the way to an angle of 90 degrees, that means our opposite side is 1, but our adjacent side is now gone. It's 0. 1 divided by 0 is impossible. We're not going to have any data there. That's why we have an asymptote right at that line. And this is why we get the weird looking graph for the tangent function. Because anytime we get to a point where the adjacent side becomes 0, which is at the top or the bottom of the unit circle, that means we'd always be dividing by 0, which is impossible. That's why we're getting those asymptotes, because there's going to be no data there. The graph is always going to break and then restart itself again. And the same thing happens when we move in the clockwise direction. Again, moving in the negative direction, the same thing happens with those asymptotes. So again, here are the sine, cosine, and tangent functions, SOH-CAH-TOA. Memorize these ratios and we'll be all set for trigonometry. Alright, so let's see this trigonometry in action and give my Trig-a-Saurus a snack along the way as well. The bone in his mouth and his jaws form a 90-degree angle. So just for fun, let's figure out how long the bone is that Trig-a-Saurus is going to eat. And given the information that I know, the 15-degree reference angle at his jaws, I want to know the opposite side, which is the length of the bone, and I do know the hypotenuse side of 6 feet of his upper jaw. Well, this tells me that I'm going to be working with the sine function because I know the opposite and the hypotenuse, or at least I want to know the opposite, and I do know the hypotenuse. So, the sine of 15 is about 0.25 rounded off. So that means my fraction should have the same exact ratio. Something over 6 needs to be that same decimal. Well, that's about 1.5. The bone is about 1.5 feet long. Because just like any algebra problem, when we're trying to undo dividing of 6, we just multiply both sides by 6, and we've solved our problem. This time, Trig-a-Saurus really wants a big bone. So here, he's opening his jaws super wide at a 90-degree angle. This time, the reference angle is at the top, where the bone meets his front tooth at about 44 degrees. So, we're trying to figure out how long his lower jaw is, So I have my reference angle here. I want to know the opposite side, and I do know the adjacent side. That tells me I'm working with a tangent function. Opposite and adjacent. So the tangent of 44 degrees is about 0.96. So again, my fractional ratio needs to work out to be that same decimal. Something over 6 is about 0.96. Well, multiply both sides by 6 again, and that tells me that I got about 5.8 feet for his lower jaw. So let's take this one step further. Let's try and figure out how long this bone actually is. So we do have both legs of the right triangle, so we just use a Pythagorean theorem here. So the 6 squared plus the 5.8 squared is almost 70. And when we square root that, we're getting something a little bit over 8 feet long for that bone. That's pretty big. Big treat for you, Triggy. So for this last one, let's give Trig-a-Saurus a medium-sized bone. And we'll find that right angle, this time, at the lower part of his jaw, where the bone meets. And let's say that Trig-a-Saurus was able to retract his jaw in a little bit to maybe only make that be 5 feet long, and the top jaw still is 6 feet. And let's say the bone that I'm giving him is 3.32 feet long. So the question this time is, at what angle will Trig-a-Saurus Rex's jaws need to be at in order to eat this bone? This is a very different type of problem. So this time we would be able to set up any fraction of the sides here for any of our trig functions and work out that decimal, but we just don't know what that angle is. So let's just say we settle on the cosine function, which is the adjacent over the hypotenuse, which is 5 over 6. And that divides out to be roughly 0.83. So the cosine of whatever angle measurement that would need to work out to be about 0.83 if we work that out on a calculator. We're going to need inverse trig functions to help us with this. And here they all are, the inverse of all of our trig functions. Either they are noted as with a little to the -1 power, or they can be called arc cos, arc sine, and arc tan. And you'll see why we need this inverse function coming up. So why do we need to use inverse trig functions here? The inverse of the cosine function? Well, just like any kind of algebra type problem, we need to undo an operation to get at our variable x. So the way to undo the cosine is to do the opposite of it, which is the inverse cosine. And whatever you do to one side, you do to the other. So therefore, we get an angle of about 33 degrees. With all the talk of trigonometry done, I think it's time to take Trig-a-Saurus Rex for a walk. What do you think, boy? Want to go for a walk? All right, let's go. Holy moly, does this guy pull on the leash.